In this video, we're going to define something called cosets, both left and right cosets. So for the duration of this video, we're going to let G be a group, G is a group, and H is a subgroup of G. Could be the trivial subgroup, could be a proper subgroup, could be an improper subgroup, whatever, just as long as it's a subgroup. All right, we're going to define left and right cosets. So let's just get on with the definition here. All right, if G belongs to the group G, the left coset of H containing G is, and here's the definition, it's written element G times the subgroup H, and this is by definition the set of all elements GH such that H belongs to the subgroup H. Now notice here, when I use G in this set notation, G is already defined. It's defined up here. It's fixed prior to my starting to talk about this particular coset. So G is fixed, and then H is allowed to range over all elements of the subgroup. So it's the set of all elements of the group that I can get by multiplying G by any element of the subgroup H with the subgroup element going on the right. And while we're at it, let's go ahead and define right coset. The right coset of H containing G is, and this is written HG, that's the set of all HG, all elements HG, where H belongs to H. Again, G is fixed. All right, now, embedded in this definition, there's kind of a claim here that I made sort of sketchily. I said containing G, here and here. So each of these is a set of elements of the group, but how do I know they actually contain G? And the reason is, well, because H is a subgroup, H is a subgroup of G, I know that H contains the identity. So that means that G times the identity belongs to GH, and also the identity times G belongs to HG. So that means that G belongs to GH, and also G belongs to HG. So G does belong to both its left coset and its right coset of H. All right, so without further ado, let's do an example. I want to start with an example that we're all pretty familiar with. Let's use G as the integers under addition. I'll just go ahead and put this just for clarification. And let's let H be a subgroup of Z, but let's not have it be the trivial subgroup or the entire group. Let's have H be kind of an interesting subgroup. Let's have H be 5Z, and that's the set of all multiples of 5. We know that's a subgroup because adding any two elements here gives me an element of this set. That goes on forever. The inverse of every element of this subset is in the subset, and of course the subset contains the identity. So I have a group and a subgroup, G and H. So what I'm going to do now is construct the cosets of H. I'm going to construct the left cosets of H first. All right, so let's suppose that G is, let's fix G to be some integer, like 3. And of course we have our H here. And let's construct the coset GH. That's the left coset. Now because my group operation is addition, instead of writing this as like 3H, I instead write it using the group operation, 3 plus H. So this is going to be the set of all 3 plus H, all integers 3 plus H, where H comes from my subgroup, which is the set of multiples of 5. So this is going to be the set containing 3 plus 0, 3 plus 5, no comma there, 3 plus 10, 3 plus 15, and so on. And of course there's negatives as well. I just started here for some reason. So I'm going to have 3, 8, 13, 18, and so on. And that should look kind of familiar. That's like the congruence class 3, mod 5. That's interesting. What if I construct another one? What if G is 10? Then GH would be 10 plus H, which is the set of all integers 10 plus H, where H comes from my subgroup. So that would be like 10 plus 0, 10 plus 5, 10 plus 10, and so on. And again, I should indicate that this goes on forever in both directions. Well, that's going to be the subset containing these numbers, which actually, if I extend a bit, that's the same thing as this set, which is actually just the set 5z, which is H. So in this case, I have that 10 plus H, this left coset, is equal to the subgroup itself. And that's something that's generally true. If I look up here at my definition, and if I suppose that G is something belonging to the subgroup H already, then what I have here is a product of elements of H, which means this is always going to be an element of the subgroup, and in fact this will capture all elements of the subgroup. So one little nice observation that we can make is that if G belongs to H already, then the coset GH, that left coset, is going to be equal to the subgroup H, and the same is true for the right coset. Okay, so back down on my example here. Another thing that we might do is we might try constructing right cosets. So let's say G is, what have I not used yet? Let's try -9. And then HG is going to be the set of all elements of H plus -9. So it's going to be the set of all H plus -9, where H belongs to my subgroup. So that's going to be like 0 plus -9, 5 plus -9, 10 plus -9, and so on, which gives me the set including -9, -4, 1, 6, and so on. Well, really, that's the same thing as if I had done this, if I had done -9 plus H, or done the left coset GH. So in this particular case, the right coset and the left coset are the same. And that's going to be true no matter which G I pick. And the reason is because the group operation is commutative. It's because my group is abelian. So there's no meaningful distinction in this case between right cosets and left cosets. However, if I look at a non-abelian group, things are going to get a little bit more interesting. So let's do that now. I'm going to zoom out and then come over here, and I'm going to put in a little visual here. I'm going to put in a Cayley table for D4 so that we can do operations in D4 quickly without having to work out all of the symmetries. So I'm going to put in an image. This will be the Cayley table for D4. Move that up here. One thing I should note for watchers of the videos, in the past I have used D to represent the lower left to upper right diagonal, thinking that's the line y equals x, and so that's what we should call D, and the other one from upper left to lower right is called D prime. Gallian actually does the opposite, so I'm going to switch my convention to match the textbook. So D is from upper left to lower right. I'll just mark that up here. So that's D, and then D prime is this one. And the reason for that, the reason that Gallian makes that choice is that this one here, the one that we're calling D, is kind of like the main diagonal of a square matrix. So it kind of makes sense in retrospect. It's not any better or worse than my convention, but consistency is better than inconsistency. That's sort of my view of things. All right, so anyway, here we have D4. This is a Cayley table for D4. And let's identify that as G. And let's identify the subgroup H as... Actually, I don't think I want to use H for the subgroup name because I have an element of the group that's called capital H. So let's not do that. Let's instead call this K. So the subgroup K will consist of the identity, there we go, that's better, and H. That'll be my subgroup. I know that's a subgroup because H composed with H is the identity. So I just have two elements there. All right, and let's work out some cosets of K for G, some left cosets. So where shall we start? Let's try working out what R90 K is. So what is that coset? That's going to be the set of all GH, where H comes from this subgroup, and where G is equal to R90. All right, so in other words, I might simplify this a bit and write it as R90 times H, where H belongs to K. Well, that's going to be just two elements. It's going to be R90 times R0, and again, because R0 lives in the subgroup and the subgroup is on the right here, R0 is going to go on the right, and then R90 times H. And then I don't even need to use my Cayley table and know that this first one is just R90. The right one I could probably use a little help. Let's look at the row R90 and then cross-reference that with H. That's going to give me D prime. So that is one coset. And then let's do another one just for the heck of it. Let's do the coset D prime K. Okay, so again, I have group element here and subgroup here, so that makes this a left coset. So this is the set of all D prime H, where H belongs to K. Well, in this case, I'm going to get D prime times R0 and D prime times H. So this time I get, well, D prime times the identity is just D prime, and D prime times H is going to be, let's see, D prime times H is R90. Well, that's interesting because that's exactly the same set I got here. These are exactly the same coset. Interesting. All right, let's try another one. Let's see if I can do this without obscuring the table here. Okay, what about if I choose V? So let's try V times K. So again, V is the group element and K is the subgroup. This will be the set of all V, H, where H belongs to K. So in this case, that's going to be the set V times the identity and V times the other element of K, which is H. So here I get V, and then VH, according to my table, is just R180. Okay, so that's another left coset, and this time it is different from these two. These two are the same, but this one is different, and in fact has nothing in common. Okay, so these are left cosets. Now I'm going to switch colors and work out a couple of right cosets. So this time let's find a couple of right cosets, starting with K times, and I'm just going to pick an element here. In fact, let's pick V. Let's use V again. So this is going to be the set of all HV, where H belongs to the subgroup K. So this time I'm going to have R0 times V and H times V. Well, R0 times V is just V, and H times V is also R180. So you notice that's the same set that we had here. The right coset was equal to the left coset. Okay, what if we try K times some other element, like let's try K times D prime. In that case, I'm going to have H times D prime, where H belongs to K. And that's going to be R0 times D prime, together with H times D prime, which is D prime. And then H times D prime, according to my table, H times D prime is R270. Well, wait a minute. Now, looking at these two cosets, those are not the same. The coset D prime K and the right coset K D prime, not the same. So this is an example in which left cosets and right cosets don't always exactly agree. We did have one left coset that agreed with the right coset, which was this one and this one. So VK and KV were both the same. But the left coset D prime K and the right coset KD prime, not the same. So one interesting question we're going to confront in the next little bit is figuring out when it is that the left cosets and the right cosets agree, because it turns out that this is important in a process that we're going to use to construct new groups from ones already familiar to us, and that's going to be called creating a quotient group. We'll get into that in a couple of chapters, but for now we're going to focus on studying cosets.